Hello, Mahesh.
One second. Sorry, sir. 1 second, sir. Sorry, sir. I know live stream landa. Sir, yes, sir. Is audible, sir, now.
Okay, fine.
But your video is top, sir. Very top. Can you tilt down a little bit? The camera should down a little bit. Yeah.
Okay, va?
This is okay. This is okay, sir. Plus, இப்போ லைவ் ஸ்ட்ரீம் நம்ம எப்போ போகலான்னு சொல்லுங்க. ப்ளஸ் உங்ககிட்ட கொஷின் ஃபார்ம் வந்துருக்கும் நினைக்கிறேன். ஸோ அது இருந்துச்சுன்னா நீங்க போயிடலாம்.
வேணாம். என்ன கேள்வியை கேளுங்க, நான் சொல்றேன்.
நமக்கு இங்க இல்ல சார், நாங்க இல்ல சார், ஸ்டூடெண்ட் தான். நாங்க வந்து ஸ்டாஃப் தானே.
எங்க இருக்கிறீங்க? எங்க அமைச்சிருக்காங்க கேள்வி? இருங்க, ஒரு எக்ஸல் ஷீட் மாதிரி வந்துச்சு.
ஆமா சார், அந்த தான் சார்.
ஷீட் வந்து ஒன்றும் கேள்வி இருந்த மாதிரி இல்லை, நேற்று செக் பண்ணப்பா.
ஓ அப்படியே சார், ஓகே. சப்போஸ் எதுவும் கொஸ்டின்ஸ் எதுவுமே அந்த அளவுக்கு இல்லை, நம்ம ஆன்லைன்ல இல்லைன்னா நம்ம கொஞ்ச நேரத்தில் நீங்க எப்போ வைண்ட் அப் பண்ண சொல்றீங்களோ அப்போ வைண்ட் அப் பண்ணிக்கலாம்.
ஓகே, ஐ அம் ரெடி. நீங்க இப்போ ஸ்டார்ட் பண்ணா பண்ணுங்க. ஐ டோன்ட் see any questions here.
Yeah, I think 2 students are joined, sir.
Okay.
If they are asking questions, we can continue.
Okay, fine, pa. I am ready. So, Lokesh.
Hi, sir. Good afternoon.
Good afternoon, Lokesh. So, tell me, how can I help you?
So, like, currently, I don't have any question. I just want to join the session to see, like, how is the response and things.
I see. Okay. Where are you from? What are you doing? Let's have a chat.
I'm from CBRA, sir. I have attended your STTP program. Like, I am from CBRA, CSA CBRA.
Oh, I see. Okay, okay. From Roorkee.
Yeah, Roorkee, yeah.
Okay, very nice.
Jan 22-24, I have attended that INSCAT program. You have come and gave the presentation in IIT Roorkee, Noida, Greater Noida.
Oh, yeah. Okay, you are part of that. Oh, okay.
Yeah, sir.
Okay, good.
Yes, sir.
Okay.
So before you were telling this about the stability courses, I have enrolled in it. So I was following you up when you were telling in the presentation.
Okay, very nice.
Yeah.
So there are how many students are registered, Mahesh? Somebody from IIT Hyderabad is there. So, Lokesh, tell me, what are the timings? When is it being live cast?
So, sorry, sir, pardon?
Are you sitting through the videos that is being provided?
Yeah, sir.
Okay, so this is what, week 3 now?
Yeah, week 3. Yeah. So today is the deadline for completing the assignments.
Okay, very nice.
Yeah.
Okay, I just wanted to ask you, how is it going?
Some of the concepts, like, I could able to personally, from my experience, I'll share, sir. Some of the concepts I could able to catch up, and some I couldn't. So the things which I couldn't, I'm referring other videos and other materials to get the good clarity. And few of the concepts which you have repeated in that INSCAT program, so I could able to connect with both.
Okay, I see. Okay, very nice.
Yes, sir.
Okay.
Primarily on the stability and other things, I could understand much better, sir, in the program, in the NPTEL program.
Okay. The course is all about stability.
Yeah.
But let's continue what we are trying to do here.
Okay.
What we need to bridge the gap between
Okay.
the fundamental.
Sir, your voice is very low, sir.
That is our fundamental understanding. Let me see how can I increase my voice. I put it in more. I can come a little closer and talk. So our fundamental understanding objective is to ensure there is no gap between structural steel design and stability. always speak with in our two different courses. What we are trying to do is to say that it is not the thing. Both has to be connected together. So if you have a fundamental,
Okay.
you will get to know within very well.
Sir, I feel someone is talking in the background, so because of which the disturbance is there, I don't know.
Background, this I am the only person in the room. I have closed these guys.
No, sir, not in your background. Maybe from someone who have joined. I couldn't able to. Yeah. Now it's fine, sir. Yeah, please.
Fine. Okay.
Yeah.
Okay. So tell me exactly what are the questions that you have.
So related to any particular concept, sir?
In general, about whatever it has been covered in this class, yes.
Sir, to be frank, as of now, I couldn't able to like get much questions on it. I'm still in the understanding phase. Maybe by next session when we connect, I can able to ask better questions in this regard. Yeah, since it is a 12-week program, I feel like I can get more of the knowledge in the upcoming part. I could able to digest more in that.
Okay, fantastic.
Yeah.
I see that there are others who have joined. Vaidya, Rathor, and Srinivas Rao Sarvade. Okay. Oh, 631 students have enrolled. Wow. Okay. And how many are going to take the exam? That's more important.
Me, sir.
No, I'm talking to 20 registered. Okay, I'm talking to Mahesh, who's basically from NPTEL office from IIT Madras.
Oh, okay. Sorry, sir.
So any questions from Vaidya? Vaidya, can you switch on your camera so that I can have a face-to-face meeting? Say likewise with Lokesh.
Yes, sir.
Okay, hi Lokesh. Okay, I know you.
Yes. Yes, sir.
Remember you? Okay, in that office, no, Delhi NCR office.
Yes, sir.
Good, very nice. How about Vaidya, Rathor, Srinivasa Rao? Okay, I'm not so sure. Okay.
Yes, morning, sir.
Morning.
Yes, my name is Srinivasa Rao. So I have completed my master's and then I'm a professional in structural steel engineering.
Oh, very nice.
We do mega projects worldwide, having almost like 28, 30 years of experience.
Fantastic.
Since stability is a very important topic in structural steel engineering, and it was not offered in Indian universities, much of it. So
Right.
I have taken this NPTEL and then trying to get on the fundamentals and the concepts. But one of the things what I just wanted to maybe you may be aware of it that American Institute of Steel Construction have an autonomous body called the Structural Steel Stability Council, which offers an extensive subjects on stability, the instability, and also the buckling requirements, and also they offer many night schools and also webinars wherein the practical aspects of the stability in terms of erection engineering, shoring engineering, timber engineering, or any mega projects where we do extensively take care of the stability bracings required. So I think if you can bring in more expertise on the or more examples of the real life problems where we come across, that would definitely rejuvenate us and then encourage us to look for similar subjects.
Okay, so that portion is covered in the last class or week 11 or 12, where I will be giving some examples on plate girder construction, things like that, especially with related to steel bridges. Okay, that was my PhD topic. So I have some real life examples on that, so which I will share it with you at week 11 or 12. So week 1 to 4 will be columns, week 5 to 8 will be beams, and week 9 to 12 will be plates. Right? And so I will be covering that. The fundamental emphasis of this course is to have an understanding of how these equations came so that you will be understanding the limitations of these equations, when to use, when not to use. Many times people do not have a fundamental understanding of that. And they treat structural steel design and stability as two different entities. It is my gut feel for the last quarter century that they are interconnected, they cannot be separated. You have to understand, and to stability to understand steel, and steel to understand stability. Both go hand in hand together. But almost all the faculty members that I've seen, I've studied at 3 different countries and 3 different places, right? Most of the knowledge that I gained on stability was from my advisor, Professor Eni Shanmugam from National University of Singapore. And the other person who taught me was Professor G.M. Hong and Professor Richard Liu. They all taught me steel and stability. So what I've understood is that you cannot separate the two, although it is taught as 2 different courses. And most of the codal provisions around the globe have commentary on steel design. That commentary will give you basically where they got the equation and how to use that equation, especially limitations of these equations. Unfortunately, in Indian code IS 800, we don't have the commentary. That makes it very, very difficult for somebody who is in India to design a steel structure with confidence. And so we need to bridge the gap and tell where these equations came from. That doesn't come from heaven, that comes from rigorous mathematics.
Absolutely.
So I wanted to take the fear out of the people who are designing steel structures. That is my number 1 goal, because fear leads to ignorance. Because people do funny things by increasing the factor of safety if they don't know anything, right? So that's what one of my professors told me. If you know what you're doing, it is factor of safety. If you don't know what you're doing, it is factor of ignorance, right? You multiply by 50. That situation should not arise, and making it still, not competitive enough. So the objective here is to create a wealth or a knowledge base so that you can understand structural steel design in IS 800 in its entirety after going through this course.
That will be great, sir, because this is a very interesting subject because you're covering the plate girders, you're also covering the stability requirements for steel structures. Because throughout my career, right from the masters, having done mega projects, we do projects in United States, projects in Middle East, Europe, very little in India, but there we have got a very established codes available. So those commentaries and then the Euler columns or the graphical solutions, what we get is very well established. Whereas here, when we go through sessions, we felt that okay, this is lacking in India, and then that is becoming a bottleneck. Though this stability course will really enhance our understanding and doing the job first time correct.
Is a background. Somebody.
Yeah.
Yourself, please. Simran Singh, I think.
Yeah. So going forward, maybe if I get a chance, maybe when I interact or if I happen to be in Hyderabad, maybe we can exchange some topics of the Structural Steel Stability Council. Also has published many stability topics for the columns, for the beams, and also for practically how they analyze the stability problems and how to read from the code of standard practice. I think that also we can exchange, and then that can be based on your enlightened understanding. You can always educate us and then take this, make this course more meaningful and more enchanting.
Sure, I would be happy to. I've been associated with SSRC from 2003. So it has been 22 years almost. My first time I visited there. So I practically grew up in the US. I did my master's, Ph.D, and basically worked for several years. I'm also a licensed professional engineer in the state of Alabama. So
I've seen that. I saw your, that expertise. Really, definitely, because I see. We see that they are very, very well advanced on the structural steel domain. They've gone miles ahead, and in India, still we are yet to take the baby steps. But going forward, I think, but these kind of subjects will definitely give us more impetus.
That is, I agree. The fundamental reason is that, in curriculum, there is too much discrimination or bias towards concrete. That is very obvious. You teach undergraduate concrete, and then advanced concrete, then pre-tensioned concrete, then post-tensioned concrete, then pre-stressed concrete. And you also talk about, something else called the retrofitting of concrete structures. So then if you talk about steel, then one subject you talk in steel and then you wind it up. So stability is not even taught in many classes. So that becomes a fear factor for people who have less knowledge in steel to take up projects in steel. And steel is much more rigorous. So that bias should be removed upfront, in my opinion. So there needs to be a revamp of the curriculum. The entire curriculum is more biased towards concrete, but concrete is now a very well understood subject. Every engineering college teaches it. But if you look at steel, there are very few people who actually advocate steel as a material of choice for construction. And to be honest with you, that's the most viable material that God has given for us to practice sustainable engineering. Because once a steel, it's always a steel. And to understand steel in its entirety and to design structures, multi-story structures, a fundamental understanding of stability is needed.
Yeah, we encounter many of these practical problems. Like, we do tilt-up panels, we do medical office buildings, where we get erection confirmatory from the erection team. Requirement where to. I hope you are able to hear to my.
I hear you, but I don't see you.
Seconds, I think some problem with my. Yeah, we get this entire temporary bracings for the tilt-up panels, which are more of like ground +3 or ground +2, and then medical office buildings where we get the approved stability requirement, because when we design an entire structure, but when we build from part to whole. So many of the stability requirements need to be adhered to, which the erection team may not be aware of it, because of which we see many instability requirements during construction, excessive sagging, and of course, sudden collapse and sudden damages. So during our whatever I learn from this course, I will be able to implement that in my day-to-day jobs, because we have large teams doing mega projects for many large data centers, large medical office buildings. It gives us an understanding of why they went for this stability bracing and how this can be erected with accuracy, with safety as well.
I completely agree with you. Again, I tell you, my PhD was in stability of curved high girder bridges during construction. So I went to a construction, how they erected the entire bridge. I think some background noise is there. Somebody can mute it. Coming from Murali Lakshmi, something like that, Lakshmi Narayana. Okay, fine. So what I'm trying to say is that yes, we can do that, but there are two things. The first thing is design. The next thing is constructability. Okay, this course is not about constructability. This course is all about design, understanding the design codal provisions first and fundamental. Then we can offer a next course where we will go into something, because as you rightly said, design does not take into account the partially completed structure, right? The stability of a partially completed structure is not taken into account. So the entire structure in its entirety is taken into consideration for design. But I think once we understand this, we need to take baby steps. Once we understand this completely, what are the do's and don'ts for a steel structure, especially during design. And after that, during construction, we can have a separate chapter that will, separate course can be offered, 2 or 3 credit course talks about the constructability. For example, I'll just tell, because my expertise, over the period of years during my doctoral studies was in bridges. There is something called deck pour sequence. So when you pour the concrete on top of a steel bridge, right, plate girder bridge, you need to know where to put the concrete. You cannot just dump the concrete at several locations. So they will identify places where there will be negative bending moment. They'll also identify places where there will be positive bending moment. So they will identify phase 1 of dumping of concrete, which is in the positive bending moment region. And then 2-3 days later, once it is partially composite action has been established, then they will pour at the negative bending regions. If you pour uniformly, then it will lead to cracking of the surface of the deck. The 230 mm deck will start to crack, and the crack will actually have a lot of bad consequences, especially in countries where there is a tendency to put salt to remove the ice. Because the bridges are crucial component, they tend to put salt, especially in states like Minnesota or the northern part of the US. They put salt, and the salt will ingress inside and will start eating your rebar. And that's one of the reasons that now the GFRP rebars in some sense have come into picture, right? So these things can be avoided if you follow the deck pour sequence. And that is part of constructability. It is there in the AASHTO guidelines. So these things can be addressed in a separate course, but this course that we are talking about is purely based on understanding and stitching the relation between steel design and stability, that both cannot exist separately. It has to be a combined effort to understand both steel and stability together to become a better design engineer.
Yes, sir. One request I have, if you can also support us by sharing the course content, which in fact I've given the feedback to the NPTEL course organizers, so that will be able to, and then wherever questions are there, we can
We are sharing that in the entire
ask and understand more clearly.
Yes, we are going through that. We will have some kind of a software where the entire material that you're talking about will be done. So we have a set of TAs who are working on it. Once it is completed, we'll share it with you.
Okay. Thank you, sir. Namaskaram.
Thank you. Where are you from?
I live in Bangalore, and then we have offices all over Hyderabad in almost 9 locations in India, and then 4 locations in US.
Oh, fantastic, fantastic. If there is any help that you need in terms of checking of any of the designs, don't hesitate to contact us.
Sure, sir. I heard that you are good in bridges, because we do almost 10 to 12 devotees. We are subscribed for doing the Department of Transportation bridges, majorly structural steel and large plate girders, almost like 20 feet, 25 feet kind of plate girders with the entire interstate corridors we do for many large fabricators in US.
Oh, fantastic. Not only bridges was my passion during my PhD, but here I'm working mostly on sustainable construction practices. So tall buildings or buildings using cold form steel, any of those things. So basically I'm focused on steel intensive construction, be it buildings, bridges, stadiums, and anything that is related to that.
Sure, sir. Thank you, sir. And I need to head for another meeting. I will log out. Thank you, sir.
Thank you. So now can I ask anyone else? I think Virendra Tiwari, Murali, Lakshmi Narayana, is there any questions that I can help you answer?
Hello, sir.
Yes.
Yes, sir, I am Mansundran. I am from Punjab, and I even attended the STP, which was conducted at GNEC Roorkee.
Oh, very nice. Thank
Yeah,
you.
yeah, I am the Sardar guy, the only Sardar guy in the whole STTP. I think maybe you remember me. So, sir, I wanted to ask that in stability, the course which is being hello,
Hello.
am I audible, sir? I think there is some other person also speaking, or there is some background noise. Hello?
Hello. Yeah, please tell me.
Yeah. So, sir, I was just asking that the course which we are doing on the stability, is it equally applicable for the RCC also, or it will be only relating to the steel structures only?
See, RCC does not primarily have a stability issue because it is big and bulky.
Okay, so basically this course will be like mainly dealing in the buckling criterias.
Yeah, basically, when you talk about steel, either it is going to be yielding or buckling. Right? So yielding is the decided mode, but buckling is an undecided mode. But the undecided mode can be converted into a decided mode by bracing or doing some kind of thing, or you have to live with the devil So what are the things that you should do, how to use the equations, where these equations came from, and things like that.
Yes, sir, I just completed the week 1 of this course, and in that I came across the buckling of the can. Sorry, not the can, actually the thin cylindrical shells.
Okay.
And I just wanted to know that how that is different from that finite buckling or bifurcation buckling, and why the thin cylindrical shells has been termed as a different buckling altogether.
See, shells are different because it is three-dimensional nature. Everything else is two-dimensional. So if you look at it, columns and beams are basically two-dimensional structures, one-dimensional. Plates are two-dimensional and shells are three-dimensional. So shells are very, very sensitive to imperfections, and sometimes the can reduce up to 70%.
Yes, I saw the graph in that. Yeah.
Right. So basically, so you have to construct shells very, very carefully. And that is why it is so much important in aerospace engineering. So if you're working for ISRO or any place, basically the rockets are all made of cylinders, right?
Yes.
So their imperfection has to be controlled, and the failure mechanism, if it is going to be buckling, then you need to have a better understanding of that, right?
Okay.
And that buckling failure is called Coke can buckling or oil can buckling, something like that. Okay, and this is not only applicable to this one, it can also be a shell. So it can also be applicable to oil tanks. So during my previous life, where I was working as a structural engineer in a power company, we used to design, for example, tanks, large tanks, and the fuel provisions were based on API, American Petroleum Institute. So we would actually design that, and we would be going for that.
Okay.
So that kind of buckling is important. So there's several different types of bucklings are there. This is one such buckling type.
Okay. I was confused that why this has been characterized as a whole different point actually.
So because it's a buckling.
Okay. So basically it's a 3D buckling, three-dimensional.
Yeah, every shell is a 3D buckling.
Okay.
It's much more complex than that. So, but our IS 800 does not cater to 3D buckling. I mean, shell buckling. That may come under specialized structures, but we were introducing the concept of stability. I don't want to give a wrong impression that stability is only about columns or beams.
Okay.
We give the entire gamut in the introduction course, and then we'll slowly build down to the three fundamental important things, which is weeks 1 to 4 is columns, weeks 5 to 8 is going to be beams, and weeks 9 to 12 will be on plates.
Okay. And one thing more, sir, I wanted to ask in the LTB, lateral torsion buckling, and that was discussed in the STTP also. And the thing is that it's a very regular practice that in pre-engineered building structures, the purlins are giving the support to the rafters. We consider them as giving the torsional as well as lateral restraint in the modeling part, and we design it with that. But in the same course, the professor from IIT Madras, Satish Kumar sir, he said that that is not fully correct. You should be having some other member giving the restraint to the rafters, but you can't consider the purlins to be giving restraint to the columns or rafters. Sir, what's your take into that?
See, it all depends upon how much stiffness it is being provided. Okay, so basically the amount of stiffness, if it is not sufficient to introduce the second mode of buckling, it is not useful. Right, you give something to you connecting the purlin to the rafter, right?
Yes.
Right, so if the connection between the purlin and the rafter is not sufficient to enforce, right, is it correct? So it depends upon the stiffness. That's why they go for fly bracing.
Yes.
If you look at any PB structure, go look at the top. They'll be having a V-shaped member.
Yes, that's flange bracing we do. Yes.
Fly bracing, FLY bracing. I don't know why they call it, but that is how they call it.
Okay.
It's called bracing. So the flange connect the top of the flanges. So basically, if you're providing adequate restraint in the compression flange, that will introduce or induce the second mode of buckling, then it is good. So you have to calculate the stiffness required to induce the second mode of buckling.
So basically, we have to calculate the stiffness of the angle members which we are using as the fly braces.
Whether that is sufficient enough to force the member that is under concentration into the second mode of buckling.
Okay, so one practice doing that is like what we do is we calculate the maximum bending moment coming in through the rafters, and after that we apply the MyFi equation, the bending equation, and we calculate the stress. And from that stress, with the use of the area, we get to the force which will be given to the flange braces. We usually give only 2.5% of that.
Yeah.
Yes, in the flanges. That is the general practice we do in Punjab. So, but the main thing is that I'm always concerned that okay, in the case of the rafters, we can say that it is possible, but in the columns, the top portion of the column is always having tension on the outer side and compression on the inner side.
Tension on the outside and compression on the inner side.
Yes, if we see on the as a portal frame, the upper part, the part where the rafter and column is connecting, that part, the column is always in the tension from the outer side and the compression in the inner side. And in that, the side railings or the girts are always connected to the outer portion only. And what is happening is they are directly connected to the tension flange. But we restrain it with the flange bracing only. We have a similar kind of arrangement for the as we have for the purlin to the rafter. We give it from the girts to the column also.
The side sheet wall is what you're talking.
Yes.
Yeah. Basically, purlins and girts are one and the same. If you put it on the rafter, it is called a purlin. If you put it on the column on the side, it is called a girt.
Yes, exactly.
Right?
And what is happening is that in rafters, we can consider that it is being, giving restraint to the compression flange. But in the columns, predominantly, where the maximum bending moment is there, in that portion, compression flange is not directly attached to the girts, but the tension flange is directly attached to the girts. Is it really possible that such a small member of purlin, like in the cold form members, can give that much restraint to that much bigger column?
That's why there is a famous paper called "The Fundamentals of Beam Bracing" by Joseph Ura. So if you look at it, it is published in 2001. It talks about all different types of bracings and the requirement for bracings along with the design examples. If you go through that, it will clearly state what is the amount of stiffness that is required. And what is most important is not only the stiffness, but also the strength that is required to force it to the next mode of buckling is what we need to calculate. But one thing is very clear is that if you connect it to a tension flange, it is not going to do anything.
Yes.
To the compression flange, because that's a dangerous fellow. Compression flange, compression member, compression part is where I think you need to put all your eggs. So then look for those things and design the structure appropriately. So I clearly cannot say this is good or this is bad, which side you should put, but I can say for a fact, that it is the compression side that needs your bracing, not the tension side. Okay, so but without knowing the entire details of the structure in question, how the loading is distributed or changing. But what you can take into consideration is understand what is the requirement of force in terms of stiffness as well as strength, and where these two things have to be better understood for you, and based on that requirement, you focus your efforts on the compression flange and brace the compression flange such that
Hello. Hello, you got disconnected, sir. I think your voice didn't clear.
Okay. Does that answer your question? I'm saying that you should check for strength,
Hmm.
you should check for stiffness,
Hmm.
and then you focus your efforts on the compression member, compression element, which is the flange, compression flange.
Okay, so my focus should always be on the compression flange restraint.
Yeah, compression flange is the fellow who will create trouble. This entire course on stability is only about one fellow, which is compression.
Yes, that is the devil.
Don't believe anybody when they say that they have a stability issue on a tension member. Tension member will never have a stability issue.
Yes.
Okay, so almost always we should focus on the compression element. We should focus on what is the strength required, what is the stiffness required to force the next mode of buckling, and appropriately design it.
Okay, sir. I'll be reading that Ura's paper because I think in N. Subramanian sir's book also that paper's reference was given.
Yeah, but you go to the source.
Okay.
Joseph Ura is someone who had worked in this area for more than 50 years.
Yes, I read somewhere. Maybe you only told that he devoted his whole life to the bracings only.
Yes, he devoted the entire life to bracing. I have met him in person.
Okay.
Fantastic individual, right? You can see his paper that is published in 1970. It's a world-class paper on column buckling.
Okay.
But for beams, he published another paper in 2001.
Okay.
The name of the paper is Fundamentals of Beam Bracing.
Fundamentals of Beam Bracing by Joseph Ura. Okay, sir. I'll get on it.
Sure, thank you.
Thank you, sir. Thank you very much.
Any questions from Manav, Murali, Lokesh?
Sir, like it's not a relevant question to the NPTEL, the course that we are getting, but in general question, I would like to get clarified on. In India, particularly, this hot rolled steel and cold forms are is it like people are telling like whatever the welding? Suppose I'm going to make a hollow section, right? A square hollow section. People are saying like even though it is hot rolled, once the temperature of that comes to the room temperature only, we'll go for welding. So it is ideally considered as cold form. Like, is there any primary difference that will come in this segment?
No, basically, there are several differences between hot rolled and cold form. The first difference is the manufacturing method. Right, hot roll with this desired shape. So whatever you get in IS 800, right? IS 808. Say for example, IS 600.
Okay.
This kind of section comes from hot rolled steel.
Okay.
Cold form steel comes in a thin sheet of metal. Right. So
okay.
Metal is basically from 0.45 mm to 3 mm.
3 mm. Okay. Okay.
And then from the sheet, you're cold bending it, and hence the name cold form.
Okay. Okay.
You are using the member whose thickness is from 0.45 to 3.0. It is called light gauge cold form steel.
Okay. Okay.
Light gauge refers to thickness. Cold form refers to the manufacturing process.
Mm-hmm. Okay.
That is very basic difference between hot roll and cold form. Right?
Okay. Okay.
But there are other fundamental differences between cold form and hot roll in terms of failure modes.
Okay.
For example, hot roll steel will fail only in local buckling or global buckling.
Okay. Local buckling or global buckling.
Global buckling. But
Hello. Sir, am I audible? Hello.
just want to design a column.
Sir, I'm so sorry, sir. I lost you. Like your connection got lost, sir. I'm so sorry.
No, did you write that it is local, global, and distortional in cold form?
Yeah. Okay. Hello.
Three different buckling modes.
Yeah.
Local.
Okay.
Global buckling.
Yeah.
And distortional buckling.
Distortional. Okay.
That is for cold form.
Okay. Okay.
You have local buckling and global buckling. That's it.
Okay. No distortional in hot roll.
power distortion, hot roll.
Okay.
Right? If you want to design a column, hot rolled steel column, you know what you need? You need a piece of paper, a pencil, a calculator, and a code book.
Okay.
That's all you need for hot roll.
Understood.
But for a
Okay.
you need a paper, pencil, calculator, code book, as well as a computer with a software that gives you the critical buckling, elastic stress, critical.
Hello. Sir?
The software
Okay.
is called thin wall.
Okay. Thin wall. Oh. Hello. Hello.
So you need
Sir, like I feel there is a connectivity issue, sir. Like I don't know whether I'm just facing a. Can anybody else confirm this, please? Hello.
can you hear me now? Can you hear me now?
Yes, sir, we can hear you.
Okay. So I was telling about the difference between hot roll and cold form, right? So hot roll steel, you don't need a computer and a software. In cold form steel, you need a computer and a software to design. That's a very important difference.
Okay.
The third difference is in cold form steel, the failure mechanisms are little nasty because it could tear like a sheet, especially connections. Cold form steel, hot rolled steel will not exhibit some of the failure mechanisms that cold form steel will exhibit. So the mode of failure in hot rolled steel and mode of failure in cold form steel is very, very different. And
Okay.
the time in hot rolled steel, it is the interaction buckling is very low. Whereas in hot rolled steel, the interaction buckling between local, global, local distortional, local, global distortional, this kind of interaction buckling modes are very common. So your understanding of cold form steel requires a very thoughtful process.
Okay.
But you cannot understand cold form steel in its entirety if you don't understand hot rolled steel, which is the mother.
Understood, sir. Okay.
You have to understand the mother to understand the child.
Okay.
Right? So hot rolled steel is the mother. So IS 800 you have to understand carefully before you go to IS 801, which is the cold form steel code.
Got it, sir. Okay. And like the 3 recommendation is it is recommended or any choral provision is there, sir? Like we should not go for more than 3 like that.
No, you can go for beyond 3 Let me clarify that.
Okay.
But if you bend it for 90 degrees, then you will stay getting cracks. So when you say, for example, you go to any football stadium or cricket stadium, you see huge light mast, right? Mast.
Yeah.
They are all cold form steel only. You know what is the
Okay.
thickness of cold form steel? 1 inch. 1 inch is equal to 25.4 mm, right? But that is
Okay.
also cold form steel, but that is not light gauge cold form steel.
Okay.
Light gauge means that it is 3 mm.
3 mm. Okay.
You have cold form steel, you don't bend it to 90 degrees, you bend it to 120 degrees. So then it is okay. You can increase the thickness and bend it to 120 degrees. And then you can form C channels, 2 C channels in a very octagon shape, and you put it together, you get an octagonal shaped tubular section, which you can use for light mast. But
Okay.
for bending it to 90 degrees, you should restrict your thickness to 3 mm so that you can
3
make
mm.
a 90-degree bend. If you increase the thickness and make a 90-degree bend, you will get a crack. Once you get a crack, then that's the beginning of end.
Okay. Sir, when this particular difference in scale, like for the composite constructions, like which one will be preferred? So, like for we can go for hot roll or cold form. Like what is your opinion on that?
See, it depends upon what your client requirement are. If
Okay.
you're going for a 60-floor structure, I wouldn't recommend cold form.
Okay.
If you're going for 8 to 10 stories, cold form is fine. See, you need to use when to use. You cannot use AK-47 to kill an ant.
That's good. Okay.
You know, you need to choose your right strategy for different types of structures.
Sir, and I heard from you, hope I saw, like for cold forms, like welding is like a different category apart more than hot roll, right? Like different procedure need to be followed.
Welding has to be done using what is known as cold metal transfer welding, which we are working on.
Okay.
So that has the limited heat input, so your heat affected zone will be restricted. Same welding technique that you use for hot rolled steel may not be viable for cold form steel.
Cold form steel, okay.
Think of it as like a electronic weighing machine that you use in your jewelry shop, and then it is used in your kirana store. You cannot take both of them electronic weighing machines. So I can use that whatever is there in the kirana shop in a jewelry shop. Jewelry shop, the sensitivity of that weighing machine will be very, very delicate. It will take even 1,000th of a microgram.
Okay.
But in a kirana store, such equipments are not needed. Such accuracy is not needed. You are going to purchase pulse and rice in 1 kg or 2 kgs, right? So you need to know where to use what.
Okay. Sir, and this Charpy test and other kinds of tests that we do for hot roll, is it also same for cold form or?
Yeah, Charpy, yes, exactly. It all depends upon your impact resistance, right? If you're going to use your cold form steel to places where it is going to be extremely cold, then you should have a Charpy V-notch test performed.
Okay.
Okay, good. Any questions?
Fine,
from
sir.
any?
Thank you, sir. Thank you.
Sure. I see that Robert is there, engineer Robert, Achampong, Vaidya Rathor. Anybody? Any questions?
Sir,
It is
just
good. We'll talk for another 10 more minutes, then we'll say and we'll meet in the next session.
sir, I just want to extend something on the cold form members only.
Mhm.
Sir, I saw your YouTube videos and there you have been you told that cold form members, what Americans did was they did the equations for axial forces and they just suppose that in bending also that will be having the same behavior.
Mhm.
But I think you challenged it and you proved them that no, you are doing something wrong, that bending has to be catered in a totally different way.
Absolutely.
Yes. So I saw your that video, and from that video I have come up with a question that when we are doing the purlins or side rails as cold form members,
Huh?
and predominantly we are having the bending actions only,
Huh?
and those bending equations which are given in the IS 801 1975, is that the way to go, or is it something that the equations which are developed by you?
No, the point I was trying to make is for built-up sections. Okay, in built-up sections, okay, especially in wall panels, most of the design provisions are based on assuming that the wall panel is subject to axial compression. When you have axial compression, it leads to minor axis buckling. Right? But the same wall panel, when it's subjected to flexure, okay, it will not undergo the same type of buckling. It will undergo what is known as LTB, which is lateral torsional buckling. So if a column is subjected to axial compression, three things could happen. Number one, it could undergo flexural buckling. Number two, it could undergo flexural torsional buckling. Number three, it could undergo torsional buckling. Okay. Depending upon your cross section, whether it is singly symmetric, doubly symmetric, and whether the shear center coincides or not. If an I section is subjected to axial compression, the I section is doubly symmetric, where the shear center and the centroid coincides. When you apply an axial compression, then it will undergo only minor axis flexural buckling.
Yes.
But if the same cross section is not an I section, but it is going to be a channel section, where the shear center is inside, now the shear center is outside and the centroid is inside the cross section, there is a difference between shear center and centroid.
Yes, there will be twisting.
There will be twisting. Why is that twisting? Because when you apply the load inherently will possess an eccentricity when the shear center and the centroid will not coincide.
Yes.
So that will lead to twisting. And that will lead to what is known as flexural torsional buckling. So it has the characteristics of flexural buckling and characteristics of the torsional buckling. And the third section is, say, for example, if you have a cruciform cross section, which is plus-shaped in cross section, and you apply the load, then what will happen is that it will, in addition to, it will not undergo flexural buckling, but it will undergo purely torsional buckling. Means that you are applying the load on the axis, the member itself will be stable, but the elements of the member will buckle, okay, thereby introducing what is known as torsional buckling as a result of your axial compressive force. So you are applying an axial compressive force, nothing happens to the member, but the elements of the member will start to rotate, and this is applicable to only one cross section, which is called cruciform cross sections.
Yes, the soldier piles cross section.
You have three different things. One, you can undergo, the member can undergo flexural buckling or flexural torsional buckling or torsional buckling. Okay, this has been very well understood. Okay, and people have all over the world have done experiments, including the people in the US who have done experiments on columns. Okay, but what I am very much against is that such understanding does not truly reflect to when the same equations are used for flexure, wherein the flexure, the members are subjected to lateral torsional buckling, which means that it will start to twist. When you apply the load, only the top portion will start to twist. And the failure mechanism is very different. Why is it different? In a member that is subjected to axial compression, the key element is to put sheathing on both sides. If it's a wall panel, you have a steel stud, full form steel stud, you put sheathing on both sides and you put the screws. The bone of contention is how to calculate the stiffness of the screws. The screws are going to provide you stiffness in X direction, which is Kx, stiffness in Y direction, Ky, and stiffness in the rotational, which is Kphi. Right? So I can remove these screws and then I can put the stiffness Kx, Ky, Kphi instead of the screws, which will simulate my loading condition, the failure modes. Right? But the American code says that a screw is a screw. It does not depend how it is loaded. So these are the set of the equations that are used for determining the stiffness of the screw. Use these equations, put it in CUFSM model, and get the values and you design for it. Which is where I differ. Whatever they have done, I am saying that it is excellent for axial compression because the failure modes are very well predicted. The screw undergoes what is known as cutting shear. Okay, the screws are going to be completely engaged 100% of the screws. Whereas when you are putting the same wall panel that is constructed using the screws subjected to flexure, the screws will not experience the same amount of force or the resistance offered in a column, because in a beam, the majority of that would be tilting effect, because the section wants to twist. And the screw stem is not subjecting itself to complete bearing, where it is subjecting to tilting effect. When a member is tilting and the screw is actually unable to prevent tilting because it is not designed for tilting, it is designed for bearing, you cannot use the 100% effectiveness of the screw that is transformed in terms of the stiffness Kx, Ky, and Kφ, which is calculated based on the American Iron and Steel Codal provisions.
Okay.
So that is the fundamental difference that I have been talking about in terms of the wall panels, which is a built-up cross-section. And we have published close to 15 to 20 papers on those areas where we have highlighted it and we have proved to them, and they have accepted that. The good thing is that such design provisions are now going to be available in IS 801, the latest version that is going to come, which is known as the direct strength stiffness method for designing of cold form steel wall panels.
Okay. The wall studs which we are having in the IS 801.
Exactly.
Okay. Because when I saw that lecture, I thought that if this is true, I think 801 is obsolete now and we need to do something else now.
No. 801 is obsolete because the last revision was done 50 years back. I mean, last code of written. It was first done in 1975, and every time it is getting just okay, and then people are using it. Okay. But it has been almost 2025, right? So 50 years have gone by. Now we have written the code, it is in its final stage. We are hoping you will get it very close, quickly. And once that is there, I think you can start using your Indian code. But until that time, it is better and wise on your part. If you want to design any cold form steel member, please use the American codal provisions.
Okay.
Except that place where there is a built-up section that is not correct flexure.
Okay. So basically, if I want to design the purlin, I should be designing it with the American code, and if there is wall stud, then I should wait for your latest code, which is going to come.
You don't have to wait for my latest code. Everything that I am telling now is published. It is available in public domain.
Okay.
So we have written book chapters also along with the design examples. So you are welcome to download it, read it, understand it, and then put it in practice. We have scientific, solid technical data to back up whatever we have written.
Okay.
Does that answer the question?
Thank you, sir, very much. And now I know that for purlins, I need to go to the American code for the time being.
For the time being, yes.
Yeah. Thank you.
Indian in the heart, global in spirit.
Yes, I remember your every line on the STTP.
Yeah. Good. So, anybody else have any question? I'm looking at some. Stability of steel. So, Robert is asking, I work with power company and review a lot of except that in transmission tower, Robert, you are using an angle section, right? And sometimes you may also use a channel section because you kind of have a belt around the transmission towers every once in a while. And understanding that, how to design it, basically you have to go through IS 800 or any other code. But here the focus is for you to understand the design provisions, how the equations came, and then you can go from there. I hope I have answered your question.
Okay, sir. Thank you.
Thank you. So why don't you just show your face so I'll know who I'm talking to?
Prof, I'm driving. That's why.
Any questions from anybody? Okay.
Prof, can you see me?
Okay, very nice, Robert.
Thank you.
Thank you. Any questions from anybody? Okay, so Mahesh, are you there? Okay, looks like he's busy. So if you don't have any questions, so we'll call it a day and then we'll look forward to meeting you in future sessions. Okay, so thank you. You have any questions? Anybody have any questions? Okay, if you don't have any questions, thank you so much. I'll log off now and we look forward to meeting you in another session.
Thank you, sir. Thank you.
Thank you. Thank you.